streaming here. I don't have, I lost my little microphone. I haven't been able to find it yet, but I think my laptop should be recording me, so we should be able to be in business here. More vocabulary. What does fixed mean?
Everyone gets the same.
Everybody gets the same. Yeah, the fixed effect is in common for everyone. What does random mean? Everybody gets their own. So when I add a random slope, I am allowing one new term in the model that is a variance across people. What it is the variance of is the individual deviations of your slope from the fixed slope. So how far off your slope is from the one that's predicted by the fixed effects, that's the random effect for each person. It's always phrased as an offness. So we had, let me pull up a slide here real quick to make an example. So without any predictors in the model, let me pull up, say, a random linear time model here. How each person in this model gets their own intercept and how they get their own linear time slope is parallel in structure. Fixed plus random, red plus blue. The fixed is the average, and then U is how far off yours is. So in thinking about longitudinal models, this type of model is a very important baseline. So once you get all of your fixed and random effects of time in place that you would need to control for change of any kind, then these represent as much random effects variance as there is to be accounted for. So this is like a new baseline. I think of it as an unconditional model for time, meaning no predictors other than effects of time. So this would be as much random intercept variance as there is. This is as much slope variance as there is. And then the question is, why do people need their own? And that's what person level predictors are for. So let's see. So we had an example with a person level predictor here, this one. Adding in, say, education. And if we add in education as a main effect, as a level 2 predictor, it should reduce the random intercept variance. What we're saying is that part of the reason people needed their own intercept is because of differences in education. So once we give each person a new fixed intercept based on their education level, U is how far off you are still from the fixed intercept. And likewise, this term right here, gamma 1,1, is education by time. So after putting this in, U1 is how far off your linear slope is from the one that's predicted by your education level. So the job of these level 2 effects is predict these level 2 random variances. If this random variance isn't here, then they predict the residual instead. I would love to. So the job of level 2 fixed effects is to predict level 2 variances. A main effect of a level 2 predictor should predict level 2 random intercept variance. And a cross-level interaction of a level 2 predictor like education with a level 1 predictor like time should predict the level 2 variance in the level 1 effect. So in this case, I have a random time slope right here. That's what education by time should be predicting. If this random time slope were not in the model, if we had tested it, declared it to be non-significant and didn't keep it, then what education by time would have to do is predict residual. Residual is where the random slope variance would have come from in the first place. So it's like it's still kind of there.
But the residual is at level 1.
Yes, it is.
So how do we can't regress technically a level 2 variable to level 1.
That is correct. So education as a main effect could never explain residual variance. Because residual variance is, why are you off your line today? Well, I have a PhD every day. Some days it doesn't feel like it. But the fact that I have a PhD does not explain why yesterday was different than today. However, what can explain residual variance at level 1 is education by time. Because by drawing a better time slope as a function of education, that can explain why you are off your line. It's because you're getting a different line, which could reduce the residual variance. It's the cross-level interaction. So yes, level 2 variables on their own cannot explain level 1 variance. Level 2 variables interacting with level 1 variables can explain level 1 variance if there's no level 2 variance for it to do instead. So in theory, this would be here, and this explains it. If this were not here, the only thing that it has to be able to do is explain residual instead. Here's another piece. If I put time in the model, which variance should it explain? Level 1 time should explain what kind of variance? Residual, that one. Yep. What is going to happen to the random intercept variance if the residual variance at level 1 goes down? It increases, yep. So whenever you explain level 1 residual variance, the level 2 random intercept variance is going to go up. They're yoked together because the level 2 residual variance has a correction factor that causes that to happen. What happens if you see a level 1 predictor reduce level 2 intercept variance? Can that happen?
If it happens, then they were smushed.
That's a smush, exactly, yes. So that was yesterday afternoon. If a level 1 predictor reduces level 2 random intercept variance, you have a case of smushing. The only way that a level 1 predictor can reduce variance above it is because of the hidden variance within it that is actually at that higher level. So daily stress cannot explain why some people have a higher mean outcome than others. But person differences in the extent to which some people are more stressed than others across days, that can explain why that outcome is higher on average. It's the embedded level 2 variance that's doing that. And so you're assuming that that embedded level 2 variance has the exact same fixed effect as the embedded level 1 variance, and that is the problem with smushing.
One thing I've struggled with in listening to you this morning reminded me of, because we petition carefully within and in between supporting smushing, the use of the word cross-level is something I struggle with, because you statistically it's impossible to have a cross-level. Right?
No.
You can never regress a variable from one level onto a variable from another level. You know, 100 onto a 10.
Let me
The
find.
intercept and slope and the variances are aggregated statistics. Right? Am I understanding that correctly?
I was with you until like the last sentence. Can you say that one again, please?
Well, when someone says, you know, you have a cross-level relationship, they're never regressing a level 2 variable 1 to a level 1 variable. Like the level 1 is aggregated up as either an intercept and slope, and then now they're both at level. The DB and IB are at level, both at level 2, or they're both at level 1. So is the term cross-level, is that a misnomer? Because I always see it in quotation marks. And is it because theoretically we might have a cross-level relationship, you know, leaders influence individual attitudes and and I know this is what level, I'm not including the same concept apply. But statistically, I can't progress 100 employees satisfaction level onto the 10 leaders score.
Correct.
I've got to either aggregate up or aggregate or disaggregate.
Yes. Okay, yes, I think
The
I'm,
question is,
yeah.
is cross-level a misnomer technical, or am I thinking about it completely different?
I think we're using the same word in two different ways. So let me clarify. When I say a cross-level interaction, what I'm talking about is just that I have a level 2 variable interacting with a level 1 variable to create a new fixed effect. And so this you can do. What you're talking about, I think, is a cross-level, like a level 2x predicting a level 1y, or a level 1x predicting a level 2y. And that, you're correct, cannot happen. The only way that you can have a level 1 variable predict a level 2 variable is the level 2 variance in the level 1 variable doing the prediction. And the other way too, the only way that you can have a level 2 variable predict a level 1 variable is the level 2 variable can predict the embedded level 2 variance in the level 1 variable. Can I put up a picture? Yeah, it's I don't think I have quite enough coffee to say that with words, so I'm going to need a picture here. Just a second. This is going to be example 3, but it will help, I think, clarify what we're talking about. So this is an example we'll have for today, looking at multi-level mediation. So we have 5 occasions within 105 people. And on each occasion, we ask them, did something stressful happen today, yes or no? What's your negative mood like today? And how crappy do you feel? Physical symptoms. So inherent in each of these variables then, even though we're thinking of them as time varying, these are daily variables, to the extent that people behave in a consistent fashion across days, they're really people variables too. So this figure is meant to convey that duality. So in the level 2 model, where we're focusing on how people differ from each other, the cross-sectional differences. Some people will have more stressor days than others. Some people are grumpier all the time than others. And some people feel crappier than others all the time. They're sicker. So those are level 2 relationships that we can examine. Do people who have more stress than other people, are they grumpier than other people? And if they're grumpier than other people, does that make them feel worse than other people? Down here though, after partitioning out that constancy, we're left with what is truly level 1 daily information. Do you have more stress than usual type of information? Do you have a worse negative mood than usual? And do you feel sicker than usual? So if you think about how does stress predict physical symptoms, it can do so in 2 different ways. But whether or not I have a stressor today cannot predict across levels why I feel sicker than other people. But whether or not I have a stressor today, to the extent that my mean stress is extrapolable, there's my word again, to the extent that having a stressor today means that I have more stress than other people, it's that more stress than other people can predict why I'm sicker than other people. So yes, the second part of what you were saying, this cross-level, no, that can't happen. It's a very common way to phrase it, but I think like the more specific way, so I can give you an example in cluster data that I just came across looking at a grant proposal where they were saying, you know, teacher blah, blah, blah is going to predict student outcomes. Nope. Because all the students have the same teacher. So teacher blah, blah is a constant within a classroom. And it's pretty hard to make a relationship out of a constant. What they meant is teacher blah, blah, blah will predict why some classrooms on average do better than other classrooms. teacher blah, blah, blah will predict the teacher level 2 variance in the student outcomes. That's what they meant. That's not as snappy of a specific game though. But the same is true here. So in the context of mediation, this gets tricky. So what if I had this box is gone? Let's say that this is like treatment versus control. If I were interested in testing mediation, the extent to which my treatment improves this thing and its improvement in this thing that changes that thing, that mediation logically can only happen between persons. There is no within-person mediation possible. Treatment versus control cannot predict why I feel sicker today than yesterday, because I was in the treatment group both days. So going back to this idea of smushing, in the context of this picture, if I don't differentiate person differences in stress from daily differences in stress, if I put them in the model as one thing, then I'm saying that this path right here and this path right here are the same. That's the smushed effect. These paths are on different scales. So for that reason alone, they're not going to be the same most of the time. Above and beyond, just conceptually, should these effects be in the same direction of the same magnitude? Okay. Long answer. Did that help? Okay. So let me talk piles for a second, because I think that's also helpful to think about in terms of what the model is doing. So this is slide 47, more review. So once upon a time there was an E. There was only an E. We split it. More specifically, when we tell the software that this is a longitudinal outcome or a multi-level outcome, when we switch from a single level model, which means we have only one kind of error term, to a two-level model, which means we have two different error terms that are unrelated. So that's what level means. It's sets of errors that are unrelated to each other. Now we have level 1 residual variance and level 2 random intercept variance. In making this distinction, in partitioning this variance, we are not explaining anything. It would not be appropriate to use the word explained variance or accounted for or R-square or any of that. We have made two piles, but the piles should add back up to be the same in balanced data, or very close to it. The purpose of this split is so that we can test effects of predictors belonging to each more accurately. So if you think about what the role of a predictor would be, time, if time is purely within persons, if time is balanced and everybody starts at the same place, a fixed effect of time logically can only possibly explain residual variance. Between person random intercept variance is constant mean differences. A variable for time can't explain constant mean differences, and so its standard error should not include this variability for which it is irrelevant. So the purpose of these partitions is twofold. One is to make it so that the predictors are tested only against their relevant pile or piles. And two, this split introduces also a covariance between the observations from the same person. This thing shows up in the off diagonal of the matrix as well as in the diagonal. So we would calculate R-squares or pseudo R-squares for within person time. So a pseudo R-square would be how much of this variance specifically did it get. A total R-square would be if I correlate the predicted values from time with the original ones, how much of the total variance put back together again did it get? Okay, with me so far? So then after we add fixed effects, we can test whether each person needs their own. And in adding those random effects, what we have done is further partition variance. Random effects do not explain variance, they make new variances. They reallocate them. Part of why people were off their line is because at this point everybody had the same parallel line. But if your line needs a different slope, that's going to reduce the ease around your line after you get your own slope. So part of what we thought was just level 1 within person noise is actually systematic to the person, is actually because some people need different slopes. And this would be true whether the slope variable in question is time or stress or any other time varying predictor. It's the same idea. So we took what was level 1 residual variance and split it partially into level 2 between person slope variance. So when all is said and done, we have one level 1 variance and we have one or more level 2 between person random effect variances, each of which represents a different reason for person dependency. And because they're all person things, they all get covariances. And that's the thing we have to add into the software that's not a default. Okay. How are we doing? Yeah, so this past year I've started taking piano lessons. I'm 40 and I'm taking piano lessons. And it's something I've always wanted to do, and I finally got around to doing it. And it's very, very humbling. I'm actually quite bad. But it reminds me what it's like to be a student. And I never, ever show up for my piano lesson perfectly remembering everything we went over last time, despite my best efforts. And I'm very sensitive to words like, oh, we already talked about this, don't you remember? Like, no, my teacher doesn't say that, and I will never, ever say that again in front of the class. So yes, review is good. Learning is hard. Sitting here all day is hard for both of us. So what else can I help go over again or fill in gaps or otherwise clarify?
So I have a follow-up question across level 1. If a level 1 predictor does have an impact on level 2 variables, or level 1 variable and level 2, does that mean that you need to partition those variables into 2? So that we've got the essential part?
Yes. So the question was, if level 1 predictor does predict level 2 variance, does that mean you should partition the variance in the level 1 predictor to avoid smushing? Absolutely. Let me go to the other one, pictures. So this is a picture of smushing sort of graphically. On the Y side, we let the model differentiate level 2 random intercept variance from level 1 residual variance. If we have a time varying X, we should be concerned about doing the same. But if you don't, if you just put in the time varying predictor all by itself and give it a fixed effect, that fixed effect has to do the work of 2 different effects. Each of its variants is supposed to have the same impact on the outcome. So it's for the same reason that we're here about the Y side, like longitudinal modeling is because I have a longitudinal outcome, I have to do all this extra random effect stuff. On the X side, same problem. And there are multiple ways of solving the problem that we're going to talk about today. So in the world of observed variable partitioning, if you leave your original X predictor in at level 1, you can solve the smushing problem by adding the level 2 mean. So in this context, if I have time varying X, I add person mean X as a level 2 predictor. These 2 variables are correlated, which means their unique effects represent different things than their total effects. But what happens is that the X effect at level 1 becomes the within. It still has variance at level 2 in it that's going to predict some of this level 2 variance. And so the person mean variable picks up the remainder that was not extrapolable from level 1. And that remainder, that incremental extra level 2 effect is what's known as the contextual effect. And if you're saying, what? I will point you back to my preferred way of thinking about these things, this one. If we partition the variance ourselves ahead of time, what's known as person mean centering or group mean centering, then we make observed versions of the model-based analogs on the y side. So person mean x has only level 2 variance. It can only have a level 2 between effect. Level 1 within person x, the time varying variable minus the person mean, has only level 1 within information. It can only have a level 1 within effect. Can't screw it up. If you leave either of these out, you assume that its effect is 0, the same as if you leave any predictor out of the model. So we did, at the end of the day,
Can I ask a quick question?
yeah, sure.
If you use the brute force on the right there, you get the same results. Yeah. So within person mean level 1.
You won't get exactly the same results. So by the way, the brute force on the y side, that's called slopes as outcomes, and that's what people did in the 80s before this stuff was invented in software.
So it's
Yeah. Yeah, so this is foreshadowing. Like, why are we letting the model do it on one side and we're making boxes? Ugh. So that's where we're headed today is, what if we did circles on both sides? How does that change things? That is a preferred approach in some respects. So the kinds of effects then that you can have, within is the effect of more than usual. Between is the effect of more than other people. Context is the difference. So within plus context gets to between. Between minus within is context. Contextual effect is the extra effect of the person after controlling for the level 1 predictor. The between effect is the effect of the person not controlling for the level 1 predictor. And we are going to see how the same model set up differently can give you either of these without you necessarily knowing otherwise. Okay. Yes, sir.
In your previous graph, when you're distinguishing between circles and boxes, aren't you doing exactly the same thing on both sides? So I don't quite understand why one are circles and one are boxes.
Conceptually doing the same thing, mathematically not. So the boxes are meant to convey that we create observed variables, and we put those in as predictors in the model, which means we're thinking of them as perfectly reliable. On the y side, it is estimating variances. You can think of those as latent variables, so the fact that they're circles is not a coincidence. And it understands that the random intercept variance is an estimated quantity. It's not perfectly reliable. It understands how much data went into it. And so if we were to predict the individual use for each person, the ones that are less reliable, the ones that are based on fewer occasions per person, or the ones that are more discrepant than the others, they would actually get pushed to look more like the mean. So there's some built-in considerations when it finds the variances that are different than when we make it have them as observed variables.
But if we decided for some reason to treat the x is our dependent variable and the y is independent variable, And we do exactly the same things if we switch circles and boxes because of the mathematics.
Yep.
Is that correct?
Yep. Yeah, it seems arbitrary when you put it this way, doesn't it? This is foreshadowing. Yes.
I ask a general question.
Hmm?
We talk about level 1 to level 2 one time. No, it's level 1. So how do we tell what predictors are level 1 and what are level 2? And sometimes it can be exchanged or like age and gender or seems like they're at the same level as probably for level 1. Sometimes one of them can be better than the other.
So the question was, how do we tell what level a predictor is? Intraclass correlation. So if a predictor is measured once, it is level 2. Even if you think it should change over time, if you don't have evidence of that, you have to treat it as time invariant. So in the example that we had yesterday, I had mother's attitudes about something is measured at age 12. Like that's how I would have to talk about it in the results and discussion is, you know, at age 12, blah, 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 because that's an acknowledgement that the mother's attitude, if measured at a different age, might have changed. So I'd have to condition my inference to be that time specific, but if I measured it once, it's level 2. If you've measured it more than once, that's where you have to figure out what kind of variance it has. And in the context of time, if everybody started at the same point, then time is level 1 only. If you have unbalanced data, there's a chance that you could have a little bit of level 2 variance in it because of that unbalance. Like if some people consistently came later than others, then like their mean time would be slightly higher. Also, if some people had missing data, their mean time would be lower than someone who had complete data. But in general, if they all came when they were supposed to and they started at the same time, then time is purely level 1. Otherwise, I would do the same thing for a level 1 predictor that I would do for any level 1 outcome. First step is an empty model. See how much variance it has at level 2 and at level 1, and if it has some of each, then you really do have to start thinking about it as 2 different variables. Whether you set it up that way to literally make those 2 variables or whether you let the model do it is a different question. But you have to think about its effect as being 2 different things. Others? Yes, sir.
So I'm nervous in the context of longitudinal data, and you have a predictor, basically future data predicting past data. So you call it mean-centered, person-centered variables. So basically using future data to figure out the mean of that person. And you're then using that to, I guess you're really only predicting maybe I'm confused, but it still seems like you have you're creating a variable that's entering your model, you know, that's future value. And maybe I'm thinking it wrong. Maybe I'm just talking something.
So it makes you uncomfortable that the person mean is incorporating later occasions to build that mean, but yet is predicting earlier occasions? Yes, I can see where that would make one uncomfortable, but in the absence of any external information that would characterize the person on that variable, that's, I think, the only logical way to do it. Now, for instance, that's a separate measurement question. So if I want to extrapolate how stressed out you are, I can ask how stressed you are each day and then come up with your mean. Or I could ask you directly, how stressed do you generally feel? And that might be a different answer than what the aggregate of your daily information is. And that, one might argue, is a better estimate to ask them directly, and I might put that in instead of the person mean in that case. I wouldn't person mean center because it's not the same variable, but that how are you generally question would provide a contextual effect to try and differentiate between within in that case. So that would accomplish the same goal as making the variable measured at both levels, maybe with less squishiness about it.
It would be the same thing if you had a random sample of students who could classes.
Yeah, exactly. So in the people in groups, taking the group mean, you really have to believe that your sample is representative of the group as a whole. And if it's not, then getting some outside information that characterizes the group more thoroughly would be a better choice.
And then you wouldn't use that. For that group setting.
Yeah, then you wouldn't do group mean centering, and then you'd have within and contextual effects, essentially. Other questions? Okay. Then we looked at person mean centering and grand mean centering yesterday in the univariate programs. I wanted to show you what the same models would look like in M+ as well. So would you like to start there? That work? Example 2B. It should be the landscape handout. Looks like this. So I have the same model. So it's an equivalent model using person mean centering for the level 1 predictor, as well as using grand mean centering. So model 2C is the first one here. This is the one that used person mean centered negative mood. I did all of my variable manipulation elsewhere and brought in a stacked data file that had the outcome, time varying negative mood, the person mean centered level 1 negative mood, the person mean of negative mood, as well as my gender variable. So going in this model then are the outcome, the two mood predictors at level 1 and level 2, the gender predictor, and because I'm also going to examine how the between person effect of negative mood differs by gender, that is an observed variable interaction that I have to create. So I did that down here in define. So this interaction term I can enter directly in SAS or SPSS or Stata. I have to make the variable in M+. And when you make new variables using define, they have to go at the end of the list and use variables or it will yell at you. Otherwise, it looks similar to the example that we saw yesterday. My level 2 variable is ID. On within, I am listing my within person negative mood so that it understands it is a purely level 1 variable. I'm listing between, or person mean negative mood, sex, and the person mean by sex interaction as between variables. So these are level specific then. Under model, there are two sections. There's within and there's between. Let me pull up the equation that goes with this because I think it's helpful in making sense of that. So this is the equation that describes the model we're fitting. Note that I have this beta 1 term right here that holds as a placeholder what the within person effects of negative mood are going to be, and the within person effect of negative mood is specified up here, as well as its interaction with gender. So this beta 1 is a placeholder. Analogously, this within person mood is beta 1. It's a placeholder. It is a name that defines the within person effect of negative mood on glucose. So you can name this whatever you want. Actually, you could name it literally whatever. 8 characters or less. So the only parameter that is actually being estimated in the level 1 model right now is this right here. That is the level 1 residual variance for glucose. That would have been in the R matrix. That's my E variance. By the way, in M+, when you make comments, that's what these little green nodes out here are. You don't have to put semicolons at the end, but I am so used to that in every other program that I just do it anyway. So sometimes you'll see them and sometimes you won't, but that's just whatever I felt like typing that day. So then everything shows up in level 2. So it's the same really as the equation. When you look at the equation, the only term that's actually in level 1 is E. Everything else is defined by placeholders that then get specified at level 2. So here's my between level 2 model. Things in brackets are the fixed effects. So glucose in brackets, that's my fixed intercept. F int is the label that I have assigned it that I'm going to use later. Likewise, within person mood in brackets is the fixed effect of within person mood at level 1. So this is confusing. Why is a level 1 fixed effect part of the level 2 model? It's a level 1 fixed effect because what it is the fixed effect of is a level 1 predictor. It is defined in the level 2 model so that you can have level 2 predictors interact with it as well as have random variance around it. So here's its label. When I list a variable or the name of a placeholder by itself, I am referring to its variance. So glucose here in the level 2 model is the random intercept variance for it. So glucose in the between is level 2 random intercept variance. Glucose in within is level 1 residual variance. Within person mood at 0 is needed to shut off the default random slope variance that all placeholders get. And I did that because in our example, I had tested whether that random effect should be here, and it was not significant, so I didn't keep it. How are we doing so far? Am I going too fast, too slow, or just right? Just right. Oh, thank you. All right. This one. Placeholder on gender. This is my cross-level interaction. It is how sex moderates the within-person affective mood. Sex at level 2, within-person mood at level 1. So whenever you want to have a level 1 effect either be random over level 2 or interact with a level 2 predictor, you have to set it up this way using this placeholder syntax to define its fixed random effects and cross-level interactions at level 2. Then these are the effects on the intercept. Person mean negative mood, simple main effect of gender, and their interaction, each with a label. Note that my labels start with an F because I don't think you can use the same word in a label as you used for a placeholder, or at least it will be confusing if you do. Okay, questions on that?
Just to clarify, glucose is random what now?
No, glucose is time varying. Yeah, it's the next morning's glucose, but it's on the same line as the previous day's mood.
So going back to the question earlier, does the program, I think I know the answer to this, does the program keep track of I mean, is the mood and glucose on the same day, they're tracked by that slope? In other words,
Yes.
you're not going to have a mood on day 5 and glucose.
Correct, it's because they're on the same row of data. So in this When you're on this side of M+, when you're using the between within, it does not have access to the other rows. It can only fit relationships for data on the same row, which is actually one of its limitations. If you wanted to have day 5 predict day 7 and have those kinds of relationships across time. Okay. So now down here, model constraint is the analog to writing estimate statements or test statements. It allows you to make linear combinations of any estimated model parameter, including variances, which is super handy for certain models. But what I have done here is create a list of fixed effects that I know what they all are. Some of them are directly given by the model, and some of them are linear combinations of model terms. But I think of this as my trail of breadcrumbs for when I look back at this like 2 years from now and I'm like, what does this mean? I have this section down here where I already did the work to figure it out. And so this is meant to map on to what I have here in each of these programs, how you ask it to estimate linear combinations of fixed effects. So it's the exact same set of effects in the same order. So the things that are not given by this model are any of the effects for women, as well as contextual effects. So we are using person mean centering, which means the level 1 effect is the within effect, the level 2 effect is the between. So for instance, the within person effect for men is defined as the fixed effect for within person mood. So that's right here. Because men are the 0, the fixed effect of within person mood is specifically for men. The within person effect of mood for women is what it is for men plus how it differs for women. So FWP M-sex refers to the cross-level interaction of gender by within person mood. So what it is for men plus how it differs for women gets us to what it is for women. Likewise, the between person effects to get to what it is for a woman, what it is for men plus how it differs for women, as given by the between bisex interaction term. And the contextual effects are the differences. So between minus within equals contextual. To get the contextual for women, it's between minus within plus how between differs for women minus how within differs for women. This is chapter 8, by the way, in the book. Go through all this algebra. This was super fun to figure out, let me tell you. Now, do you need to report this in your life? Probably not. Why am I showing this to you? Because in certain ways of setting up the models, this is what you get instead. So I want you to be able to go back and forth, no matter what M+ gives you, to get either the contextual or the between as you want. And so if you compare the results of model 2C, which is on page 8 of example 2A, you can put those next to the ones from M+, and see how they map on. This is literally the same model, just with different software. So the within level, what it labels as residual variance is the level 1 residual variance specifically. In the between level, if you go down to what it calls residual variances here, what would I call this one right here? What is that? I call that random intercept variance left over. That's what it means by residual, left over. What is this thing? And should I be concerned that it has a confidence interval or whatever, a p-value of 9999. No, I should not be concerned.
You said it.
Because I said it, yeah. So this would have been the random slope variance left over in the within person effect of negative mood. This would have been the level 2 random slope variance left over in the level 1 effect of within person negative mood. There. But I didn't estimate it, so it's set to 0. Here's intercept. What is that thing? This is the easy one. The actual intercept, yes. And it has a t-value of 181. Do I care about that? No, it just means that the conditional mean of glucose is not 0. So no, I don't care about that. But yes, so this is what I would call the intercept. This is the fixed intercept for glucose, gamma 0, 0. This thing is also under intercepts, but what's that? Give you a hint, something to do with mood. Hmm?
Beta 1.
It is it's the fixed effect of mood in beta 1, exactly. This is the fixed effect of level 1 negative mood. They put it in intercepts because it is conditional on an interaction. It's being predicted by gender. So this is the within person negative mood effect for men.
If it was not being predicted, they would label that a mean.
That's correct. And if it's not being predicted, it would be under means, as would my fixed intercept in an empty model. Yep. So an intercept is a fixed effect that is being predicted by something else. A mean is a fixed effect that is not being predicted by something else. Analogously, a residual variance is a variance that is being predicted. A variance is just a variance that's not predicted. And then the ons, these are all fixed effects. What's the first one here? Feel free to read from the screen. I'm shameless in soliciting participation. Within person mood on gender. That's my cross level, yep. That is gender differences in the level 1 effect of within person mood. So this is how much less positive the within person mood effect is in women. So here's what it is in men, 0.03. Up here tells me how it differs for women. So I would say the within person level 1 negative mood effect is less positive in women, significantly so. And last but not least, the 3 effects on log glucose, those are things that predict beta 0. So the fixed intercept is 4.9. That's for a man on an average day. For every 1 unit higher in person mean negative mood, average glucose for men goes up by 0.2. Average glucose among average moody people is non-significantly lower for women. And the between person effect of negative mood for men of 0.2 is significantly less positive, significantly weaker in women by 0.18. And the results section at the end of 2A, by the way, has all these words. And here are the results of the new parameters. So this gives me all of my fixed effects of interest in one place. What it is for men, what it is for women, and how it differs. And the things in bold are the ones that I had to ask for as linear combinations of model parameters. Okay, questions?
Can you trust those p-values?
Well, good question. This is using maximum likelihood. This is a sample of about 200 people. So I would say yes, to the extent that we can believe that glucose has normally distributed residuals at level 1 and level 2. Yes-ish. If this were a small level 2 sample, I would be a little more hesitant because we're not using any denominator degrees of freedom and we're not using Remel. Yeah.
Intraclass has the awkward grouping center option. I'm assuming that's not something you ever use. Is it just because you wouldn't trust it, or?
I've had bad experiences trying to let it do data manipulation things for me because sometimes there's an order of operations problems. Like if I ask it to do a group mean centering and then like center the mean of something, sometimes it tries to center the thing that doesn't exist yet and it tells me it can't. I would assume that it would be fine to use that otherwise. I just tend to make all the variables that I need elsewhere where I have a data set I can stare at and make sure that it worked. So. Others. So in this example, we used person mean centering because we literally carved up by brute force our time varying X variance into its level 2 and level 1 parts. The other option when dealing with observed variables is to use grand mean centering at level 1 instead of group mean centering. So the last model in example 2 swaps out that version of the level 1 predictor. So this is almost identical code except for the changes that switching the predictor implies. So if I were to use the original level 1 predictor, not the person mean centered version, but the original one. So I'm switching from using within person negative mood to using this time varying negative mood. This is the original one. So it goes here on use variables, it goes here on within, and it goes here in the level 1 placeholder effect for the within person negative mood slope. The consequence of switching the level 1 predictor lies in the interpretation of the level 2 effect. I am not smushing. I am still including the person mean, but rather than making that person mean the between effect, it's now the contextual. So down here I have switched my labels accordingly. This is the contextual effect at level 2. That's given directly by the model now, and so to get to the between, I have to add the within and contextual effects together. just realized I have a typo in here. That one should be con right here to match this term down here. Sorry about that. All these typos that I'm catching, by the way, which of course I can only catch when in front of people, I will fix the handouts and repost once we're all done here. So because I did not group mean center my level 1 predictor, my level 2 fixed effects are contextual effects, not between effects. So this effect of person mean negative mood right here, that is the extra contribution of being a grumpy person after controlling for how grumpy you are today. To get to the total contribution of being a grumpy person, I have to add this extra part to the within person effect. Within plus contextual equals between. Within plus contextual equals between. Anytime that you invoke this placeholder syntax, that is where you have to be careful what you get at level 2. So we'll see that in the examples that follow. All right, questions? All right. Okay. So I want to transition then actually into the handout that I showed you the picture of earlier and transition from univariate modeling to multivariate modeling of multi-level data. So this is lecture 3. I believe it's at the front of the other packet. So when I say univariate, I mean we are letting the model partition variance in one outcome that is measured over time. So we had glucose as the outcome. Multivariate means that we are letting the model partition the variance in more than one longitudinal outcome simultaneously. And that is the way that you have to do it in order to look at how level 1 variance in one outcome predicts level 1 variance of another, and how level 1 variance in that outcome predicts level 1 variance of another. So if you want a variable to be both a predictor and an outcome, like in a mediation model or something like that, it has to be in the context of multivariate. So this is what we just talked about, univariate approaches. So this is letting the model partition the variance in the outcome. We take the predictor and we carve up the variance ourselves. So this is the smushed effect. We don't want that. We went over that this morning. We fix it by putting the contextual effect in at level 2. And this is the person mean centered version. But as pointed out, this seems sort of arbitrary that we're making variables on one side, but letting the model do it on the other. So what if we did that? Watch closely. Camera 1, camera 2, camera 1, camera 2. Why not do it the same on both sides? To do that requires software that allows you to variance partition more than one variable at a time. You can trick univariate software into doing that if you are willing to have all of your relationships specified as covariances only. So if you just want to know, say, if the intercept on this variable correlates with the intercept on that variable, And if this random slope on this variable correlates with the random slope on that variable, you can do that in univariate software. I can show you how. But most of the time, folks want some kind of directed path. They want to be able to predict things and have the same variable potentially be both a predictor and an outcome with respect to other variables. To do that properly, both sides need to have model base. So this transition, by the way, from this to this, if you are in a job talk, folks, you have just done multi-level structural equation modeling. Just regular multi-level SEM. I don't call it that. The reason that people call it that is because they call these random effects latent variables, and so they call it SEM. To me, SEM means you have a measurement model. You have a latent factor measurement model. This is one variable. This is not a latent factor. So I reserve the term multi-level SEM for actual measurement models for between and within variance. So if this X was a factor, you could have a within factor and a between factor. That would be multi-level SEM to me. But the rest of the world will call it this. So I call this multivariate multi-level. You can also call it MSEM. So why do it this way? Well, pros of letting the model partition both sides, that makes more sense. There's also some simulation research that suggests that the level 2 effects that you get when you let the model find this random intercept variance as opposed to making it yourself with the box, that this version gives you stronger level 2 tests of your fixed effects. However, those effects are often noisier and less consistent because it has to find that variance first. So if you have a small level 2 sample size or low intraclass correlation, meaning there's not a lot of variance in the intercept to begin with, it can be hard to find the variance and to find effects of the variance. So you generally need to have bigger samples to do a multivariate version of this model than to do the brute force person mean centering. The other cons really have to do with software problems, not modeling problems. So a drawback of using M+ is that it doesn't have residual maximum likelihood or denominator degrees of freedom, so it will be less trustworthy for small samples. The other problem is interaction terms. So if you want to fit an interaction term, say, let me go back to this picture. In the model we just looked at, we took this box right here, this person mean negative mood, and we made an interaction with gender. That was an observed variable interaction. But if we're in this framework right here, I have to make an interaction of a box and a circle. That's what's known as a latent variable interaction. And to estimate those requires numeric integration. It's the same thing that makes random effects modeling computationally intensive in IRT modeling or generalized latent variable modeling. And so it can be difficult to not possible sometimes to include latent variable interactions and more than one of them. So that's where the drawback comes. All right. So let me show you what this is going to look like. We have a couple minutes and then we'll take a break. Example 3. So this is a case in which we have to switch to a multivariate model because I need negative mood to be both a predictor and an outcome. So, you folks do mediation stuff? Yeah. I am going to begrudgingly show this to you because I hate mediation, I'm just going to be honest. I think mediation is a regression with a better marketing campaign behind it. No, I mean, seriously, like it's always phrased as, well, what's the effect of X after controlling for M, right? Like that's what we ask all the time. That's a unique effect. But there's extra language that goes with this and extra importance that goes with this. So I am going to be agnostic as to all of that and just show you how to do it. So we have the use of boxes and circles in this picture is deliberate. I am going to have to brute force partition my stress variable because it is dichotomous. M plus will not let you model-based partition variables that are not normal. And I ran into an error message when trying this, and I went to the discussion board and searched for the error that I got, and you know what post came up? The one that I had asked her myself in 2015. I was like, I thought I had seen this error before. So I went to my email and tracked down the solution they sent, because her answer, of course, was, you know, send me your syntax and output and license number. So I did that. And no, it's still not possible in version 8. So when I originally built this example a couple of years ago, I thought it might be possible to tell it that this is binary and let it partition the variance, but it's still not. So for that reason, because stress at level 1 is binary, I am leaving it as the 0-1 version at level 1, and I am putting in a box for person mean stressors at level 2. So that means this path, person mean to negative mood and person mean to physical symptoms, that is just a traditional univariate approach. So you could have done that path in software. It's this one that's tricky, because this is between two estimated variances. So I have a whole lot of words here trying to describe how you put these things in the model. But the bottom line is that because I am treating these things as observed predictors, they cannot have missingness. They are not part of the likelihood. These variables, negative mood and physical symptoms, in letting the model partition their variance, I have brought them into the likelihood that they can have missing data under the assumption of missing at random. That means I have to assume residual normality for both of them to do so. So the first model, I'm looking at the relationship between stress and symptoms before controlling for the mediator. So I could have done this model in SAS, and here's the code for that. And this looks exactly like the example that we just saw. So in this data set, I have 5 occasions per person. This is a stacked data set. Symptoms is the outcome. I have covariates of women and age. So these are older adults measured across 5 days. I have level 1 stress, which is 0-1. I have person mean stress centered at 0.4. So this is the proportion of days on which they reported a stressor. So that's my level 2 mean. And I have the interaction between age and sex as a level 2 interaction I've defined here. So my cluster variable is my person ID. Within is stress, so I'm having it tell it that the level 1 stress variable is to be kept at the within level only, because person mean stress is going in at the between level, along with my age and gender covariance. At the within level, symptoms, there's my residual variance. This is the level 1 relationship between stress and symptoms, where stress is the X and symptoms is the Y. So the name that I gave that for the placeholder is within person X to Y. At level 2, here's my fixed intercept for symptoms in the bracket. Here's my random intercept variance for symptoms. In the bracket is my fixed effect for my level 1 X to Y relationship. I do not have a random effect because previous models told me I didn't need one. This is something that you would test. Here are my age and gender covariates. And here is my contextual level 2 effect. It is contextual because the stress variable that went in at level 1 is its original version. It was not person mean centered because person mean centering doesn't make too much sense when you have a 0-1 variable. So because my level 1 stress has level 2 person variance in it, the level 2 effect of the mean is the contextual effect. So to get to the between, I add the within to the contextual, and that gives me the between. Yes?
So if you didn't set the random stress slope to 0, would it just not be enough to make the model? Or would it affect other things?
If I didn't set it to 0, it would estimate it, but it would not estimate the covariance with the intercept that should also go with it. So it would affect other things in that regard. It wouldn't necessarily hurt anything to have it estimated, but models that have lots of random effects that are small are tough to converge. Other questions? Yeah.
You go back.
Yep.
So here, what happens if you do put your stress variable at both levels? So if you're told it to put it only, but if you put it at both levels, then you still get a contextual.
If I put stress at both levels, so I did, but I put person mean stress in at level 2.
So if you didn't do the person at all at level 2, what would happen? Not
I don't think you can do that. I don't think it would let me put stress at both levels. I'm pretty sure it would yell at me about that. If you wanted to put it at both levels by letting it estimate it, then I'd have to assume that it's normally distributed and it's a 0-1 variable. So then I'm unwilling to do that. All right. So here are the outputs from SAS and M+ side by side. Ignoring the effects of age and gender, since those are covariates that I'm not terribly interested in right now. The things that we would need to look for: person mean stress on symptoms. That's my contextual effect. So after controlling for whether or not I had a stressor today, for every unit more stressors I have than other people on average, symptoms overall goes up by 1.3. And that's a pretty big coefficient, but remember what a unit is going to mean here. For a 0-1 variable, the mean at level 2 is going to range from 0 to 1. So a 1 unit change is the difference between someone having no stressor days and 100% stressor days. So if I wanted to talk about it as, say, for every 10% more, I could just move the decimal over and say for every 10% more stressor days, mean symptoms across the study goes up by 0.13. On the means here, this is my within person effect of stress on symptoms. It's listed under means because nothing is predicting it. So for every unit, actually, if I go from a non-stressor day to a stressor day, after controlling for my mean level of stressors, symptoms that day go up by 0.11. However, so X to Y is not significant within persons. If I take my contextual effect of 1.3 and add to it my within person effect, I get my between person effect, which is significant. So this one is not controlling for whether or not you had a stressor. What is the effect of being a stressed out person? The one given to the model is after controlling for whether or not you had a stressor. What is the effect of being a stressed out person? They're both significant. So I do have X to Y significant at the between level. Questions? Any that you want to hear? let's take a break. I'll see you in about 20 minutes.